Um, and I'm also have an appointment at the University of Oxford that primarily is looking at sending telescopes and doing astronomy into space. So I'm going to talk about basically all of these different roles in the course of the talk, so I don't need to go through. But the next slide tries to highlight that. And as I like to say, this is a talk about all my children, because through the course of my career, my children, well, I guess not my non-human children, have been developing systems and deploying and operating radio systems. It was kind of it wasn't a deliberate thing. As an undergraduate, I was in astronomy and astrophysics at Harvard, and you have to pick a topic for your thesis. I actually started infrared, but there was the small radio telescope on the roof of the Center for Astrophysics building right across the street from my dorm that I became a paid observer as an undergraduate. And that was a small radio telescope that looked at one of the central lines that help us understand the gas and the dust in our galaxy. And that just kind of kept going as I realized how fascinating that was. I will say, after doing kind of the hardcore astronomy and astrophysics for a while, I did realize that I was much more interested in two things. One, understanding how those instruments work that collected the radiation. It was a little daunting as an undergrad to just have this thing that magically produces data and always be a little worried at 2 in the morning if it broke or if the doer needed helium and all those things. And I didn't really know how it worked and how to, diagnose and troubleshoot and fix. So after that, actually, I went into electrical engineering, and my Ph.D. is in electrical engineering from Georgia Tech, where I became a professor of electromagnetics. But again, I focused on doing planetary radio astronomy, essentially, which is planetary atmosphere sounding using radio telescopes. I did go to NASA for a short time to do that, but then came back to Georgia Tech. And this was ostensibly to start developing the telescope in the upper left of this image here, called the Woodbury Research Facility, which was an old AT&T, and as I learned, had a shady history as a NSA facility that had been decommissioned, actually quite aggressively so. And we wanted to make this telescope work for radio astronomy with the primary target of search for extraterrestrial intelligence, or SETI, which we now call technosignatures. And at the end, there'll be quite a bit of that because that's a large chunk of what I do. So this is a 30-meter telescope in Georgia. And then I developed and made it work as a nice radio telescope. And then I became a faculty member there. But then, I guess the siren sounded, and I wanted to keep building larger instruments. And I moved to the University of California, Berkeley, although I was an employee at a place called the SETI Institute, to develop this thing right next to the Woodbury picture of the Allen Telescope Array, which is a 42, soon to be 43 element array. And I will talk about that up in Northern California, about a 5-hour drive in a beautiful spot. Of course, the sirens kept sounding, and Australia had a large national facility they wanted to develop. And so I moved to Australia to lead the group developing and building a brand new telescope on a brand new site in Western Australia called it became to be known as the Australian SKA Pathfinder, or Australian Square Kilometre Array Pathfinder. And I worked on there for a while, came back to the US to do other cosmological experiments. The two in the middle are two arrays deployed in Africa. The one on the left is called PAPER, which stands for the Precision Array Probing the Epoch of Reionization. It's a great, fun acronym. It's hard to Google. If you Google PAPER, you really have to dig through the results to find that. It was decommissioned about not quite a decade ago, and became the array next to it called HERA, or the Hydrogen Epoch of Reionization Array. We actually used a lot of parts from the previous array, so in many ways we recycled paper to build this thing called HERA. On the bottom right is actually a small educational telescope quite close to me here in the Bay Area called the Leuchtner Radio Telescope. That is a fun thing I spent time developing. So I kind of call these my children. These are the primary instruments that I've been one of the prime movers and developers and operators of. I do have real children and a family and a dog, but fortunately for you, the topic is not of this talk is not that. All right, so what is the topic of what we're doing here? Well, really, it's an homage to the electromagnetic spectrum in the guise of radio astronomy. So we'll talk a little bit about radio astronomy, what it is and how we do it. I guess if you don't want to pay attention, radio astronomy is astronomy, and we use light, but radio light to do it. Really probably more relevant for this group and for thinking about it are spending a little bit of time on the signal types we detect and the signal processing we do. And then the 800-pound gorilla in modern radio astronomy is radio frequency interference. So I will end on radio frequency interference because I've actually spent a large part of my career worried about that and working on ways to help mitigate that for what we call the passive radio services, which is a terrible name because we're not very passive, but we don't generate radiation, we just receive it. My PhD advisor and then my colleague at Georgia Tech, Dr. Paul Steffes, still is a fabulous advocate of this. And very early on, he got me involved in trying to help the community doing this. And it's kind of stuck, I guess, throughout my career. All right, so this is obvious to everyone here, but it is important to remember radio waves are light too. They're just light at a different wavelength. And I actually bring this up because often when radio telescopes are brought up or images are shown, we talk about listening for radio waves. And, that's just because of the analog with the fact that you listen to a radio and listen to music. But it is just electromagnetic spectrum. Actually, I should have brought it about 15 or maybe closer to 20 years ago, the IEEE Microwave Magazine, I wrote an article for it about the Allen Telescope Array, and they developed the artwork. And on the artwork, they just showed a bunch of ears. It's probably the most hideous microwave magazine cover imaginable. And it propagates a completely wrong view of what radio astronomy is about. So I kind of hate it, but it's over there somewhere and it's just hideous. So obviously radio waves and electromagnetic radiation has essentially two properties that we typically think about and care about, the wavelength and the frequency, that are of course coupled by the speed of the propagation in that medium. And I kind of bring them up in this way because the wavelength in many ways helps us set how big the antenna has to be, right? You'd like it to be many wavelengths across, often, not necessarily always if you want to see a large chunk of the sky. So when you're developing radio telescopes, the wavelength just tells you, well, how big does this thing have to be? And then the frequency, obviously a derivative of parameter, it tells you how fast I have to sample the waveform. Because one of the great advantages of radio astronomy over, say, optical astronomy, and if I ever sound like I'm down talking optical astronomy, I'm not. It's just there are contrasts for how we do this, is that in radio astronomy, we have the ability to measure the amplitude and the phase of the wave. Optical astronomy, well, almost exclusively, if not exclusively, measures the amplitude just because, the frequency is so fast. And that limits some of the things they can do with some of the analysis after the fact. Radio waves, we use this to great benefit by we can put our telescopes quite far apart and coherently combine them to get a good view of the sky. And I'll show some beautiful pictures of how that's done. All right, so this is actually an old chart. I kind of liked it. That just shows the uses, the radio portion of the electromagnetic spectrum and its canonical uses. And I just liked it because they throw a radio astronomy telescope on there at the high frequency side. Although I do take a little bit of issue with it because quite frankly, radio astronomy is done over this entire range. There is a cutoff, and you notice it doesn't extend to the left, and that's because the ionosphere above our heads limits our ability to see outside of the Earth's atmosphere, really below 10 megahertz. And so it is above 10 megahertz or so, maybe 30. If you want to do radio astronomy there, you start to think about going above the ionosphere. So radio astronomy, we cover that whole frequency range, and it tells us different things about the universe. So you can say, well, you've got a frequency, why don't you just happy with that frequency? Well, that's because different parts of the electromagnetic spectrum probe very, very different physical processes in the universe. And really what astronomy is, it's the observational techniques to observe the universe and try to map it to an astrophysical process or something that we can model and understand the physics underneath it. And there's a lot of physics, a lot of different types of physics in the universe. And so we need all these different frequencies to understand all these different mechanisms that produce radiation. So for astronomy, most of us are familiar with optical, primarily because we have an optical telescope or two in our heads. it has the advantage. It's been around a long time. Galileo was a long time ago, and they've been doing it for a long time. But it actually deals with typically small, hot objects or stars or other compact objects that are hot enough that actually generate significant radiation at the visible part of the spectrum. Radio waves deal with typically lower energy things. Again, we're not low energy or passive. We're very active, very high energy. But radio deals with typically cooler objects in the universe, and we can deal with the thermal radiation from things like dust, as well as non-thermal energy, which a lot of what the exciting things in the universe are non-thermal sources. I will say that these things constitute most of the ordinary matter of the universe. Over 90% of the matter of the universe is probed by radio waves as opposed to optical, just because most of the mass of the universe is in gas and dust that optical doesn't really see. So I'm kind of going to go through a few of the mechanisms that emit in the radio and why we care. There's a great textbook, Rybak B. and Lightman, that goes through all these in a lot of mathematical detail, but this is hopefully a good overview. So, all right, so what in the universe is radiating that a radio telescope sees? Well, the first thing are what I call zippy electrons. So the universe is very dynamic. It's exploding. There are supernovas, black holes, they're ejecting matter in the universe. And so a lot of particles are traveling at nearly the speed of light, or relativistic speeds. And they're typically, at that point, they're not neutral matter, they're charged particles. Electrons are very light charged particles. They're kind of easy to make. And so a lot of what radio astronomy sees are electrons just streaming through the universe that have been accelerated by past cataclysmic events. And as we know, if it was just traveling in a linear fashion, we wouldn't see it, because as we know, to have a charge radiate, it has to accelerate, either change its speed or change its direction. Well, the reason why that these electrons change their direction, and to some extent their speed, is because the universe is threaded by magnetic field lines on every scale of the universe. This kind of what I view a very beautiful image on the left is actually an image from a radio telescope in space that operated 300 some gigahertz, called the Planck telescope. And its goal was actually to measure this cosmic microwave background that we spoke about at the very start, that Robert Wilson and Arno Penzias discovered. But in between us and that cosmic microwave background, which is near the origin of our universe, is our galaxy and all these field lines. So they actually have to understand what we call the foregrounds in that case. So this image from the Planck telescope shows these magnetic field lines threaded through our galaxy. And you can see they're very large scale structures, and they're everywhere. And so these zippy electrons spin around these magnetic field lines and produce synchrotron radiation primarily in our galaxy. This has a great historical precedent, because the radio telescope on the right, that didn't start as a radio telescope, it started as a Bell Labs experiment, is how radio astronomy started. And the very first start of radio astronomy was detecting the galaxy emitting the synchrotron radiation. And directly below it is the rather unexciting spectrum of the synchrotron radiation through our galaxy of these zippy electrons. This also has another great part of our story, because the announcement of radio astronomy, here you'll notice you can actually not numbered, a note on His-type atmospheric noise by Carl Guth Jansky, was presented at the 1933 precursor to the National Radio Science meeting of URSI. So radio astronomy was announced at this meeting in Washington, D.C. before we moved to Boulder for the National Radio Science meeting, coupled in with a lot of other talks, a few, and some names like Southworth and kind of stalwarts in the field of radio. But this rather innocuous A note on His-type atmospheric noise was the announcement of radio astronomy to the world, which kind of fell on deaf ears. Jansky has some great letters he sent home after the talk to his dad. He's like, well, it's just a bunch of grumpy old men who didn't really understand what I was doing, which is kind of funny. But that's the start of radio astronomy. And so URSI played its role in the announcing radio astronomy to the world. I'm not going to go much of the history, but so it did start in the US, and it kind of fell follow during World War II. But after World War II, there was all this great radar equipment that then got pointed to the sky in Australia, the Netherlands, and England primarily, and then the US got back involved. All right, so that's the start of radio astronomy and one of the key things, the loudest things emitting radio waves in the sky. But there's a lot of other stuff out there. So stuff radiates. So when you have, as you know, when you have a body at a given temperature above absolute zero, it radiates thermal energy. Dust is a body above absolute zero. It radiates in the radio frequencies. The universe as a whole, we talked about the cosmic microwave background, radiates. And so these curves here are just black body curves at different temperatures. And you see, I put a lot up here in the optical region. And you see here's the optical spectrum that our eyes are used to. And here are stars that kind of peak in these different regions. That's the purview of optical astronomers. The Earth is an infrared, primarily an infrared source. So it's kind of on our horizon. The atmosphere, of course, emits in the radio, and we can measure that. This is the universe, actually an image from that same satellite I showed those beautiful field lines from to show the small perturbations. These are perturbations on like a part in 100,000 on a DC value that map out the universe. But I'll just point out that 90% of the ordinary stuff of the universe is over here on this side of the spectrum and is the purview of radio astronomy. So in addition to these emitting bodies, the other thing that emits is gas. So as I highlighted with the Earth, we have an atmosphere that has a change of temperature across it. It also has different constituents that emit in different wavelengths and absorb in different wavelengths. So gas radiates, and in an atmosphere, we can actually use that and sound the atmosphere. That was actually my background at Georgia Tech that I was doing, was sounding atmospheres. And this just shows actually, if you look at Jupiter at the radio from low frequency, L band and below to, X band or K band, you can sound the entire atmosphere. So we can sound atmospheres with radio astronomy. And then we can also measure dust gas rather, in the interstellar medium, that stuff between the stars that emits in spectral lines. This is a key, on the top shows a water maser. The universe makes masers naturally. It's kind of fascinating that the universe makes a maser. And on the bottom actually shows a very messy spectrum at 230 gigahertz of a galaxy. And you see there's a lot of lines, and you can see how complex those lines can get and how we can measure. So we can actually assay the universe from afar, and you get these very long chain molecules that we can measure with radios. So that's a lot of radio astronomy and how we understand molecular clouds and the precursors to stars and the things that then turn on and radiate in optical. The other thing that radiates is hydrogen gas, and this is kind of the astronomer's favorite frequency, 1420, and that's the hydrogen line. The hydrogen line has this, radiates at this particular frequency. It's kind of amazing. It was predicted theoretically. There's a guy he wanted to do radio astronomy, a professor, and he was like, but I need something to look at. And he said his grad student to say, find me something I can look at. And the grad student said, well, I'll look through here. And he found this hyperfine forbidden transition of hydrogen. And then a few years later, actually at Harvard, my alma mater, they actually measured it in the universe, and it's become our bread and butter and how we understand a large chunk of the universe. It gets our wonderful little 1420 allocation in the chart that we all use and is used for Earth remote sensing a lot. And we can measure that. It wiggles with, as the universe expands and contracts, as we look at orbits in our galaxy and other galaxies, we can actually measure radio velocities. All right, so why these different radio velocities? This is probably the worst graphic on the Doppler effect, but I don't know if you heard that, but it is a very real effect, and it is kind of fascinating when you can hear it. It's quite audible to your ears when you hear it. And of course, the same things happens at radio wavelengths. In our galaxy, that hydrogen can be going away from us or coming toward us, so it can be red shifted or blue shifted. But it turns out our universe is only expanding, and so it's always red shifted. And so one of the nice things about this hydrogen gas is it permeates the entire history of the universe up till about 380,000 years to the Big Bang. That 380,000 years after the Big Bang is this cosmic microwave background that we've now brought up a few times. So this actually is a chart that shows the entire history of the universe on a log scale, showing the Big Bang about 13.8 billion years ago, kind of funny thing called inflation, nothing to do with current economies, but this really period of time where the universe expanded by many, many orders of magnitude in fractions of a second. And then it started to just expand out of there. So as that universe expands, the hydrogen gas all got formed here in this cosmic microwave background. We can see that because that's when the gas became neutral and we could actually see the radiation behind it. And so to probe all of this period, hydrogen gas, that spectral line I've talked about at 1420 megahertz is what we do. This chart here at the bottom actually just shows that cosmology has a pretty simple equation that models how this thing expanded. The hard part is getting the values for these parameters and how they change over cosmic time. So if we're looking here on the right is the current day, WMAP was actually the telescope that made this cosmic microwave background image shown. That was a US led space-based telescope. If I want to look up the 1420 megahertz line in our galaxy, it's at 1420. But as I look back over cosmic time, the redshift, the Doppler shift changes. So if I want to look at hydrogen gas at this very early time before there were even stars, I'm going to look at around 10 or 100 megahertz of frequency. And so I want to cover everywhere from 1420 to 10 megahertz to understand the universe just with that one line. And then, of course, there are many lines that can be present in the early universe. So that, I hope, motivates what we're looking at, why we want so many frequencies. We're not just greedy. We want to understand the universe. And it focuses on radio astronomy. The thing I'm not going to talk about here that in many ways is the critical app is Earth remote sensing, because Earth remote sensing uses all these same techniques to understand our Earth as a system, which is quite vital for understanding climate change, for understanding soil moisture, for understanding energetics in our atmosphere and our oceans and so on. So this really is a very critical thing. Now here we take essentially a radio telescope, point it back at the Earth and take measurements, or we can look up and measure the atmosphere. So I'm not going to talk about that, but this is an incredibly important application of these passive radio science services. I think we should probably have another talk that highlights the remote sensing. All right. So what sort of power levels do we detect and are we trying to find? So, as I mentioned, the universe, it generates energy. It's almost always Gaussian noise. So really radio astronomers, we're looking at noise, but we can measure parameters of it. So, but these sources are emitting. Sometimes these sources fill the whole sky like our galaxy's synchrotron radiation. Sometimes they're very small point sources at a distant galaxy or in our galaxy. And this chart on the right just shows as a function of frequency from 10 megahertz to 10, 15 gigahertz, a bunch of discrete sources in the sky that have been known to radio astronomy from the early days and we use, including the sun and the moon and a lot of some black holes and some galaxies and so on. And it has this unit that radio astronomers use, which is a Jansky, named after Carl Jansky. I often kind of wondered if Commission J became Commission J because of Jansky, but I think actually it was just a coincidence, but it's a fantastic coincidence. A Jansky is 10 to the minus 26 watts per square meter per steradian per hertz, so it's a very small number. So if we have our flux of a source in Janskys or power flux density, we have a telescope of a certain area and a bandwidth at a certain size, width. We know that we can receive radiation levels there. The noise is just related to our stochastic noise of the system, characterized by a system temperature. So if we want to look at some canonical levels for a radio telescope, the Green Bank radio telescope is the world's largest fully steerable structure, in fact, but certainly largest radio telescope. It's an offset, so it's 110 meters in one dimension, but it has an aperture on the sky of 100 meters and has a very low system temperature of about 20 Kelvin. So it's really one of the most sensitive things that points up in the sky. Not the most, but one of the most sensitive things. So if we want to look at a source that has a unit of a Jansky, which is a fairly strong source, there aren't many things that have a unit of a whole Jansky. There are some that have much more. And I put that in. I see that my received signal that I'm going to get from that source is about 0.03 picowatts. I use picowatts because I actually couldn't remember what was smaller than a picowatt. Um, so it's very, very small. We have a good system, so our noise temperature is quite small too, but it's quite a bit larger, many picowatts. In fact, our signal to noise ratio, if we just took those as gospel, would be much smaller than 1. So I will note that that power level is about the same as a cell phone on Mars. So a cell phone on Mars would be a fairly bright source to us, and it could get in our way. On the moon, it'd be way too bright. On the moon, it can be 4,000 picowatts or more. And as I mentioned, most of radio astronomy is done below that level. So you kind of say, well, you're kind of at a loss. Even a great system has a noise temperature or system temperature of 0.3 picowatts. What are you going to do? Well, fortunately, we can stare. And one of the nice things as we stare at these sources, the power from that source doesn't go down because it's an actual source, but the stochastic noise beats down. And so we can get a sensitivity that's just given by this very simple equation. This is somewhat simplistic, but in fact, it works over almost the whole entire range, where my noise is set by the system temperature, but then if I stare over a broad bandwidth, it goes down by essentially the number of samples I take. The b-tau product, if you Nyquist sample, is about the number of samples that you take, and it goes as the square root. So if I stare at a source for 4 hours or more, and that's not uncommon, I can get microkelvin as my sensitivity. So, those are the sorts of levels that radio astronomy worries about, fractions of a picowatt and a few microkelvin of noise. So it's quite challenging. So you say, well, great, you just stare and you can get 5 microkelvin, you stare for 4 more hours, it beats down by the, factor of 1.4 and so on. Well, there are a few problems that make it difficult for us to keep going. And that is, one of the exciting things about the sky is that it's changing, and there are transients that don't last very long. In fact, some of the most exciting, most energetic bursts in the universe, fast radio bursts, add for nanoseconds or microseconds. So if I want to understand that, I can't just integrate. And also, if I want to look at all those spectral lines I talked about, I can't just make my bandwidth arbitrarily large because I want to differentiate the spectral line versus not on the spectral line. Also, as all of you know, receivers aren't perfect. They don't, even when you throw in tricks like switching and stuff, they're not perfect. And then, of course, we have what I'm going to talk about at the end, radio frequency interference. So to get a sense of a little bit more of a sense of some of the levels, I actually just put some of the standards that show standards for radio frequency interference appropriateness, if you will. At the top is your part 15. Those are kind of your standard devices. And, we like them to not be too bad. And so they have a spec for how much emission they can generate out of their band. So that's up here. It's kind of you have to convert them all to funny units. And I think I did all of them fairly correctly. The military wants to be a little bit better. And so they actually have a standard mil-spec 461G. And it has a lot of different parameters, whether you're under the ocean or in the sky. But if you take the lowest level across the band, you get a curve that looks like this. And then there are those radio astronomers who want to understand the universe, and we have our own spec that is ITU recommendation, and that's this orange line. So you can see it's 60 dB or more below even the low noise mil spec. So it's very challenging, and that's one of the central challenges. So let me talk a little bit now about telescopes, what I build, and just to kind of motivate that as to why telescopes are located where they're at. This is kind of a cartoon that shows the transmissivity through our Earth's atmosphere as a function of frequency, all the way from gamma rays and X-rays up here to low frequency radio waves down here. And this just shows that for most of the electromagnetic spectrum, we can't see through it. Our atmosphere happily actually protects us. It protects us from ozone, it protects us from gamma, it protects us from a lot of stuff, but those darn astronomers get in a pickle. So for a lot of those bands, you send satellites above the atmosphere. So if you want to observe it, UV, X-rays, and so on, and most of the infrared, you go above the atmosphere. Fortunately for us, and it's probably no coincidence that that's where our eyeballs work. There's this band where we can see through at the visible, and that's where, the optical radio astronomy. There are the structures that we can see through and pick and choose. And then we have this kind of juicy sweet spot in the radio that the atmosphere is almost completely transparent to, and then the ionosphere. So we have these nice clear skies. These we typically want to go in valleys because the atmosphere is transparent and it shields us. These things we want to go on mountaintops because we want less atmosphere. But the problem is, that part of the sky is filling in with extraneous radiation that gets in our way. So that's my artist's rendering of RFI to a radio astronomer. All right, so looking at telescopes. So telescopes receive electromagnetic waves. There actually are, you can make gravity wave telescopes, and they actually detect gravity perturbations, but by and large, we view telescopes receiving electromagnetic waves, and our eye is a great one. It has a diameter of 1.4 millimeters. It can change, which is pretty helpful. It has a band 390 to 700 nanometers. It has quite a few pixels. It's a foveated array. It has cones and rods that can detect different things, so it's quite sophisticated. But typically, we don't view our eye as a telescope, but it really kind of set the standard for what we want to do. So what we want to, oops, oh, sorry, I thought that the picture of the eye was there. I was talking about the eye, and I wasn't even showing the image of it. So typically, though, we think of a telescope as enhancing our ability. And so at optical, we like to put them above the atmosphere. And now we can have optical telescopes that are 10 meters or more, or we can have multiple telescopes. And that gives us a lot more sensitivity. In the radio, we want to do the same thing. The human body doesn't naturally detect radio waves. We detect infrared. Our skin's actually a pretty good infrared detector, but so far no one's proposed making an infrared telescope from the human bodies. It's actually kind of, I guess, a little creepy if you think about it, so I don't. But radio telescopes, we can make these large structures that can also be used for communications. And this is the Green Bank Telescope in West Virginia, operated by the National Radio Astronomy Observatory. Well, actually, technically the Green Bank Observatory, 100-meter across, beautiful telescope that has been operating for many decades and does a lot of bread and butter. The Parkes Radio Telescope was one of arguably the second large radio telescope in the world in Australia. My group ran it. It's actually the first large radio telescope I ever visited as a backpacking across Australia. So it's a beautiful place to go and visit. And so, we look at the sky, we measure. The Arecibo telescope was the most sensitive single dish until China built a larger one. But as we know, sometimes bad things happen. And not too long ago, this happened, which was quite a tragedy. I will say the telescope operated for many, many more years above expect, but still it's disappointing when you see something catastrophic like that. So these are single dishes. So they're big buckets. You point them, they collect the radiation, you move them, you collect radiation, and you can map out the sky in that way. It has a nice advantage of it's sensitive to all spatial scales on the sky, so you don't lose spatial information, but you do have to point it and kind of build up images slowly. Fortunately for radio astronomy, we can measure the phase, and so we can make arrays. So we can have multiple telescopes that we hook together like one big telescope. This is the Very Large Array in New Mexico. Really one of the most prolific and productive telescopes ever made. There are 27, 25-meter telescopes that are all arrayed together. They operate from 0.07 to 42 gigahertz, so very, very flexible. And this is really one of the first telescopes to make some of these amazing images. This is a galaxy, a very distant galaxy, was one of the very early test images made by the Very Large Array on the left. On the right is an Australia array that I thought I had a picture of that made a nice image of early image of the center of our galaxy. The center of our galaxy is kind of low in the atmosphere, low declination, so you see it better in the southern hemisphere. So you can make these amazing images. The telescope that I'm kind of working on most these days is this hydrogen epoch of ionization array, which is trying to measure these early scales of the universe before there were stars, but the large-scale structure of the universe was imprinted on it already because of cosmological effects. So we have this array. It's 350 14-meter antennas. So the central core is 300 meters across. And then there are 30 outriggers that give us more sensitivity. It's low frequency, so it's actually built out of PVC and wood and mesh and screen, but is very effective. So I spent a lot of time there. This is just a close-up picture of what it looks like in the Karoo of South Africa. And we're taking data as we speak. That's I guess one of my more active children. Another one is the Allen Telescope Array at the Hat Creek Radio Observatory, which has 42, soon to be 43, 6.1 meter antennas. It's 6.1 meter antennas because the guy that built the dish itself wouldn't build a 6 meter antenna, but he would build a 20-foot antenna. So we have a 20-foot antenna instead of a 6 meter antenna. And it is very flexible, and it's owned and operated by the SETI Institute, and again, actively taking data as we speak. And in fact, it's being used quite a lot for space situational awareness to try to understand how these large satellite constellations are impacting interference on the Earth. So this is just a pair. You can see the 42 antennas. My mouse isn't getting over there to it. About 5 hours north of the Bay Area. We actually have another kind of cool telescope that just started working there called CHIME, or the Canadian Hydrogen Intensity Mapping Experiment, which is doing a couple different things. One of the things it's doing primarily in our context is it's measuring these explosions in the universe and helping understand, the cataclysmic events that happen across the universe. Because near and dear to my heart, but the ATA, the Allen Telescope Array, was funded initially by Paul Allen, one of the Microsoft founders. It has a very, very flexible architecture. We developed this very large band feed. The feed itself goes from 1 to 10 gigahertz, which at the time was state of the art. Now there are better feeds, and we're putting those on that go from 1 to 20 gigahertz and produce very, very low noise figures. We take that whole 10 gigahertz back on analog optical fiber and slice and dice it many different ways so that we have a very, very flexible. So you can observe at 1 gigahertz and you can observe at 10 gigahertz at the same time. You can subarray. It's quite a flexible instrument that allows you to do a lot of different science, and it is focused on technosignatures, or the search for extraterrestrial intelligence, because it's owned and operated by the SETI Institute. This is the image I showed in my title slide, and this is taken by a radio telescope, actually right next to my Hera radio telescope called MeerKAT. CAT stood for Karoo Array Telescope, and they had a small one, and they built it bigger, so it became MeerKAT, more cat. And they took another image, a new image of the galactic center with the MeerKAT telescope at L-band, and produced this image. So in my view, this is one of the most beautiful astronomical images ever done, and it shows you all the different phenomena that are going on at the center of our galaxy. You can see bubbles. Those are supernova remnants, where a star went supernova and this gas went out. You can see these swirlers that go through that are radiation going along magnetic field lines. The central thing in the middle that you can't see through in this image is the central galactic massive black hole at the center of our galaxy that another radio telescope very recently took an image of, using an array that spanned the entire globe called the Event Horizon Telescope, and got a lot of press. Radio astronomers like it when we're on the cover of New York Times, which I think has happened, once or twice. And this is one of them. So radio tells us a lot about how that works. I probably should have gotten here faster, because this is a very, very busy slide that tries to talk about how we process the data. So let's just focus on the center. A radio telescope, you can think as the sky comes in, data comes out, and then we need to process that data. And there's lots of ways we process that data. We can make beams on the left-hand side of those blocks. If we make different beams in the sky, we can actually do very high time spectral resolution and examine for periodic pulses, i.e. for pulsars, find fast radio bursts, these transient events, make these dynamic spectrum. So on the left shows some of the things that, this little black hole is supposed to, this little neutron star is supposed to be spinning to talk about pulsars. The different things that you can do with the radio telescope, looking at kind of this side. On the top is actually the Voyager satellite going through a beam. Fast radio bursts are these cataclysmic explosions. That image kind of right next to the dish is the different pulses of a pulsar. You might recognize it as a very prominent thing from a t-shirt. A musical band quite a while made a t-shirt and used that as their image, and at least around here, it gets a lot of use. And then on the right-hand side, we can also take all that together and make images, both continuum, just the thermal energy, as well as maps. And so on the top, on the right there is that beautiful image of the central part of our galaxy. And then at the bottom actually shows the carbon monoxide line over an image, over a continuum image, showing that you can now see that this thing is rotating, because on the bottom side it's red shifted, on the top side is blue shifted. So you can get all the dynamics of galaxies through radio astronomy. So we do all this thing, but the common theme throughout is that we always average in time and bandwidth. And typically over space, because we can't, we see chunks of space. So we rarely say voltages, we never demodulate, we always channelize in time and bandwidth. And that is useful for us because then we can integrate. We don't try to demodulate, so we don't get information out. And it's very helpful that nature doesn't compress in those two axes together. So if you see noise that's Gaussian, that's not compressed, it's typically going to be a natural phenomena. And so this chart just shows kind of where nature emits in these things like fast radio bursts and pulsars and galaxies and supernova remnants on the kind of upper right, and then where technology transmits on the lower left. And that white curve is actually a bandwidth time product of 1. And so we can try to use that to differentiate between natural phenomena and artificial phenomena. One of the problems is that engineers are very, very clever, and we're finding that, well, if you spread the spectrum out and make it noise-like, you can actually transmit more information. And so that curve actually keeps pushing upward and to the right and just gets more prominent, and it makes it hard for us to see. And particularly, it makes it hard for us to do something called technosignatures. This is just an image of the famous Drake equation that's up in the Green Bank Observatory, where Frank Drake kind of came up with ways, how can I quantify how many alien civilizations and look at it? And that's one of the central designs we're doing. For your information, we don't know what n is. It's somewhere between 1 and 1 million in our, or bigger. Not smaller, because we know there's 1, although it's still out to it's not known whether it's an intelligent species here on Earth, and that's up for debate. So this technosignature work is we're trying to find direct or indirect evidence of technology that's not from humans. And there are different ways you can do it. You can try to find artifacts. That's very hard. Or you can try to find transmitters that they have. We know we transmit in space. It's very logical to assume they transmit into space. There was a very famous, intriguing signal found in the 70s called the WOW signal. This was the Big Ear telescope in Ohio State. Still never explained. And this was their version of they didn't even have a chart recorder, for Pete's sake. They just plotted on a printer numbers that related to the magnitude, and you can see this sort of relates. Still unexplained, but probably not ET, but there was no RFI at the time to get confused, so it's one of the more intriguing things. Modern processing, we look more at something like this. This is actually a signal from the most distant human object. So this is a technosignature, but it's sent by humans. It's outside of our solar system and the Voyager telescope, the Voyager spacecraft transmitting back to Earth. So these are the sorts of signals that we typically look for. We want to look for more. We want to look for anything that isn't natural, but we're working on the processing. We have a lot of telescopes that we're looking at. And the Breakthrough Listen program is spearheading this, and it's a program that's now located headquartered at the University of Oxford, which is why I also have an appointment there. Whoops. So there's a lot of work in that regard, and in astronomy, but let me get to the last but. I'm probably going over time a little bit, but I'll wrap up quickly. This is taking the Allen Telescope Array and just kind of wiggling around for about 20 minutes and taking spectra. And the radio telescope is at a fairly radio quiet site. And you look at this and you're like, well, it's not at one of the best sites. So, and you can do astronomy. Well, let's go to one of the best sites. Let's go to the South African site, which is one of the reserve sites on this planet, where my Hera telescope is. And you see, we actually have to get rid of a lot of the data. If you look here, it's still pretty good, but you see for a lot of the spectrum, much of the time we can't use it. FM is completely out of the question. And And so you see all these signals that are radio frequency interference. So RFI is the problem that we try to deal with. And, we want RFI, RFI relates to using our cell phones. So this is just on these two radio quiet sites that show all the cell phone towers in the area, and you can see it's hard. And now we have cell phones from space, which mean they cover the entire Earth. We have our cars, which emit copiously. This just shows all the transmitters in a kind of a car. It's actually not done by radio astronomers or communications people. It's done by health people, because people worried about just how healthy it is to be standing essentially in a microwave oven or sitting in a microwave oven for a long period of time. We have planes that travel all over the place. They both transmit directly, but also things we transmit bounce off them. And so, signals bouncing off a plane is a very strong signal, and that was just nationally. But if you look in countries, right, there's a lot of planes. And of course, we have satellites, which used to be a problem. There were hundreds, if not thousands, of satellites. Well, now with the satellite constellations, there are tens of thousands, or will be tens of thousands of satellites. You can see this chart on the upper left shows the Starlink launches, or the number of satellites, which is essentially the Starlink launches. And you see over the last few years, it's just going up, and it's going to continue. I call them the great equalizers, because it doesn't matter where you build a telescope, you're going to hit these things. And this just shows the stuff that's orbiting the Earth that gets in our way. Even when they don't intentionally radiate, they radiate both themselves, the computers. The lower left shows very low frequency emission from a Starlink satellite. That's just incidental radiation. And they also reflect stuff. They're so bad that even the optical astronomers have a problem. This just shows the Starlink satellites going through an optical field, and they reflect light. So even the optical people. All right, so we have a lot of ways we want to handle it. We want to build a robust system. We want to detect it. We want to excise it. Mostly we excise it. We're developing techniques where we can see through it and subtract it, but mostly we just identify it and we get rid of it. And so the whole trick is identifying RFI. And much of radio astronomy processing are pipelines that detect and get rid of RFI. This plot is related to just getting rid of RFI on a recent technosignature survey. All right, so receiver design need to be robust. We can go to the best sites, but satellites are there. We can try to avoid. And all of these will improve with research and technology and policy, but none of them are going to enable technosignatures to look through it, and it will only get worse with time, as we know, and we expect, right? Society demands that we have more connectivity. So we have policy and management issues that can help control. I wrote a paper with another group of people called Policy and Management, and that's how we do it. Currently, in the middle shows kind of this international flow chart of how we try to regulate radio emissions through the ITU, through our national administrations. I'll put in a plug for the Committee on Radio Frequencies, which is the National Academy that tries to keep track of these things that affect radio science, and propagate it up through this middle flow chart. So if you're interested, and they're always looking for good people to serve on CORF. I was on it in the chair a decade or so ago, and it's important that we keep going. And of course, we have our beautiful allocation wall chart that shows how finely the spectrum is sliced and diced. But I will note that, we're going to step on each other's toes, and we already are. And I put this just to remind people that, radio astronomy might be the canary in the coal mine, because we have these sensitive receivers that probably see it first, and we don't demodulate where we can't get rid of it as easily. But, eventually everyone will be impacted. The thing I don't like about this analogy is often the canary dies. So we want to forestall the canary from dying. So we want to do other things. We're looking at something called radio dynamic zones, where we try to share dynamically. And so you have the spectrum, but you have reservations, and you have clocks, and you have policemen saying, okay, you can go here, you can't go here. And that's a very active thing that the NSF is funding, and I'm involved with. And we can go to the far side of the moon where we don't have radiation. And I'm actually designing this thing behind me is actually the prototype of an element that I'm hoping to send to the moon in the next few years to do radio astronomy there. But other people have the idea. So there are already a lot of missions planned to the far side of the moon and to orbit the moon and so on. So even that's not going to stay pristine for too long. So here we go. Here we go. Here's my thing landing on the far side of the moon with that chart. Hopefully soon. All right. So sorry, a little long, but the takeaway message are the electromagnetic spectrum is finite. It's shared. We are sharing already, whether we intended to or not. And so we need to be very deliberate how we share it. And these trends will only accelerate, being impacted by radio frequency interference, as well as coming up with ways to share it. There are many axes to share. We need to be creative researchers and try to come up with avenues to share and what might work for radio astronomy and Earth remote sensing. This National Radiodynamic Zone is one of the primary avenues being explored now by the NSF. And we need a lot of community-based tools and standards and policy in order for these passive research radio science services to continue to inform humanity, both the universe as well as our Earth. So thank you.
Thank you very much, David. Thank you. That was fascinating. Fascinating.
I can't tell if anyone left or not, so I'm assuming they're all still there
People are here.
on the edge of their seats.
People are still here. The number is about the same. So we are open to questions. You can.
I know I tend to get too excited about
in the chat, and then we will ask a question.
I know I get very excited about the astronomy and the early side, and I then have to rush through the important signal types and mitigation. But yes.
Well, let me begin by asking a question. The signals that come from wherever they're coming from in space, they are probably very noisy signals. Okay. Is it possible that when you do some sort of processing on them, that you are actually throwing out some of the baby with the bathwater?
Well, that's an excellent question. It's actually, like most things, it's not necessarily a easy answer. For kind of your canonical astronomy, where you use a radio telescope and you either make images or take spectra and integrate, in the absence of RFI, you can differentiate, right? The noise will go down as root N, and the power from the source will fix. So you can get that level very clearly. Now, with radio frequency interference, we actually have to we flag a lot of data, and we tend to be conservative because even a small amount of residual radio frequency interference is brighter than the source we're trying to see. So we try to throw away more. So we do lose data in throwing away information that way. But in terms of just the thermal noise, the thermal noise from our receiver beats down the thermal noise from the source, is a fixed power. There are other much more sophisticated techniques. This hydrogen epoch environization array doesn't even make images or spectra per se. We do a completely different processing mode. And there we worry a lot about throwing away data because it's not in an axis where you can easily pick out the noise from the signal. It's in a completely axis that's dominated by the cosmological scale of the universe. And so we worry a lot about throwing away signal unknowingly there. So a lot of the effort is just to try to characterize how much signal we might have thrown away as a max. So, but yeah, all of our signal is noise. It's just Gaussian noise, but it's a fixed, well, except for transients, we can detect that it's fixed in the sky.
Thank you. We have a couple of questions on Q&A. Jamesina, would you ask?
Yeah, well, there we go. First, thanks for a very interesting talk, and you touched on a lot of things that impact all of us working in different aspects of electromagnetics. And it reminded me of just recently a talk at NRSM where they were complaining about the signals bouncing off of airplanes. So
yeah,
yeah, very, very relevant there. I imagine the machine learning has been around for much longer than a lot of the public knows, but have you seen the transformations more recently that have really impacted the field?
That is just starting, in fact. But yeah, so it's funny, machine learning we talk about match filters, which you can design a match filter. Machine learning is sort of the same. You have to train it. So you still have the same amount of effort, but it's much more flexible and can be quite good on detecting radio frequency interference. But not a lot has been done.
but that is accelerating. And with all the modern tools that make it so much easier, about 3 years ago, the breakthrough listen community put out our first machine learning process of data. And that will only accelerate, but it's computationally expensive, and you have to make sure, again, you're not throwing out known signals or things you don't want to throw out. But I would say in terms of kind of growth in the field and where it's going, certainly for technosignatures, machine learning, AI is going to be where it's all out. Ideally, you just develop a machine that the grand anomaly detector, where it detects everything and it can categorize it and say, okay, these are the things I know, these are the things I don't, and you can look more closely. So that's kind of what we're trying to reach, but there's a ways to go. And I do know in my talk, I covered way too much territory, so very overly comprehensive.
No, it's great. Thank you.
There is a question on Q&A that I'll ask on behalf of Mr. Abdul Rahman. How do array-based radio telescopes compensate for the sensitivity of a large single-dish telescope? If arrays are more versatile, do you think that single-dish telescopes may become obsolete soon?
Yeah, well, that's an excellent question. So single dishes have kind of one advantage, and that is single dishes just detect the total power on the sky, which is easy in some sense. It's a big bucket that collects the radiation and you move it. But it means that it's a DC measurement, right? You're just measuring DC power. So for an interferometer, you have samples across an aperture, and I can measure the amplitude and the phase. And so I can combine them, the two antennas. So if I multiply the signals, the complex signals from two antennas, that's what we call the cross power. So all of the common mode, or most of the common mode, goes away. So it's much more robust for interference and basically for everything. And also I can spread them out. But now I have to be a little bit careful because I'm only detecting certain spatial modes on the sky. And if I spread them out too far to see small things on the sky, I'm missing the big structures on the sky that might confuse me. And if I pull them all together to try to collect that, I'm missing some of the fine structure on the sky that I could confuse for large scale structures. So there are trade-offs, but definitely interferometers are dramatically more flexible than single dishes. And also, you're building less things out of metal and more things out of computers, which has a good trajectory for being cost effective. So I sort of doubt there'll be many or any large antennas built anymore. Even though they do have that important advantage of being able to, they see all the power from the sky. So having a few around to measure that is quite important. They tend to not have to be as big as some of the larger structures. The new Chinese telescope is 500 meters across and is the most sensitive thing on the planet. But it's probably the last of its kind, just because, yes, arrays have a lot of advantages. We can measure that phase. It's our big advantage.
There is another question for you from Jeffrey Piepmeyer. Do you see RFI from proliferated LEO satellite constellations? Can you filter that out?
Yes, and hi, Jeff. Jeff and I were grad students together at Georgia Tech. So, yes, and actually over the last few months, most of my activity has been working with SpaceX to develop techniques for direct-to-cell to work from space. And, so we see the radiation that they intend to transmit at 1990 to 1995. In fact, you can now sign up for a free trial T-Mobile service from this service. And so, but I will say that both because the government has told them they have to, but also the companies seem interested in preserving astronomy. We've been working quite closely with SpaceX under the auspices of the National Science Foundation, which is kind of is the keeper of scientific uses of the spectrum, and the National Radio Astronomy Observatory. So we've actually implemented something called telescope boreside avoidance, where SpaceX actually turns off the transmitters if they go through our beam. So we tell them where we're pointed, and they do this. So and it's quite effective. I actually that's a very active thing for me now, and we monitor that. And that way we can observe the band they're transmitting in because we always see it, but the power is so strong it doesn't saturate our entire front end. So that's the thing we're trying to do. You want to build receivers that don't saturate, and then you want to come up with techniques where you don't look at things that saturate you, because then I can look at frequencies outside that band, even if that particular band, which is their rightful allocation, right? You know, it's their right to use that band, but we like to keep it so that they don't saturate us, so we can observe outside of those bands that are allocated to them. And they're gonna the satellites are gonna, you know, the number is just gonna keep going up.
One of the things that you mentioned, David, that Paul Allen, who was, I guess, a Microsoft founder,
Yeah.
Funded one of your telescopes. Given the news from Washington, D.C., from NSF, etc., what do you think will happen with regard to government funding?
Yeah, I will say private funding is, well, it always has been important, particularly in the US. And actually, most of my career, or much of it, has been privately funded, initially by Paul Allen. The Gordon and Betty Moore Foundation has a lot of funding for science. And in fact, the Hera telescope is funded in part by the Gordon and Betty Moore Foundation. The Schmidt Futures Foundation is funding a new telescope being built out of Caltech called the Deep Space, the DSA. The Allen Telescope Array actually now has been funded completely by one of the Qualcomm founders, who actually unfortunately recently passed away, called Franklin Antonio. So this private money, it's going to become more important, and it has been quite important. I think giving up on public funding of science is a dramatic loss. In part, you know, these private funders are, you know, very interested in the science, and they're great funding vehicles. But, you know, they fund a few things that they select. Having an open system and having public funding where much more research is funded is critical. So, you know, we certainly hope, and I guess expect that, you know, public funding will continue, but certainly the private foundations are even more relevant. And they've certainly been relevant over my entire career.
Thank you. Well, other questions?
I know we're after the hour. People are fatigued. They've listened to me yammer.
Yeah, and in fact, there are people who have joined from China and India, I've seen, and from Italy.
Oh.
They must be all getting ready to sleep. Okay. All right. Well, David, thank you very, very much. This was fascinating. And thank you.
Yeah,
James?
thank you very much. Thank you.
All right. Well, thank you for the opportunity.
Oh,
And
there is one more question. Hold on. There is one more.
Sure.
You know, it makes me think of Richard II. Question. My horse for a question, or something like that, huh? How does this from Leonard Jacques? How does the increased use of cellular and data alone affect your observations?
Yeah, so one of the things radio astronomy has basically always done is we've gone to remote places where people aren't, because all the technology, you know, impacts us. So, for instance, at the Hat Creek Radio Observatory, not through any policy really, your cell phone doesn't work, just because there's very few people and there's mountains around. So that sort of thing we still see it on the telescope, but your phone doesn't work because it doesn't have enough sensitivity. So we certainly see it. It doesn't saturate us. And again, if we're not saturated, we can find the quiet places in between and assume that, you know, there's not residual power in there. The great change, as I call these great equalizers, are the cell phones from space. And that era actually started this month, right? The SpaceX license basically enabled them to start service this month for the direct-to-cell service from space. There are more companies in line. And, you know, and then the entire surface of the Earth will be covered. So we do know, you know, from now and to the indefinite future, the band 1990 to 1995 is no longer going to be usable for radio astronomy, because anywhere and everywhere you look, there'll be a SpaceX satellite transmitting. again, which is, they have every right to do so. And so we just try to keep the saturation down so that we can observe outside those bands.
Okay, thank you. Okay, all right. I guess with this, we will end this webinar sponsored by the U.S. National Committee for Radio Science. And our speaker was Dr. David DeBoer from Berkeley and Oxford. And my co-host was James Ina Simpson from University of Utah. Thank you very much, all of you, for attending.
Thank you. Have a good rest of your day.
Thank you.
Thank you. Bye-bye.